maybe 2, 3, I don't know exactly the number. So I will be speaking about the method I commonly use, which is the, I don't know if it's too small, you can tell me, which is the folding method for thin domains with rough boundaries. So usually in this course you had the standard way of defining a thin domain, which would be something like this. So here it can be thought as R2 and an R2 domain, or a multi-dimensional domain. And what happens in these situations? Well, in my case, I usually study a lot more simple equations like the heat equation and parabolic problems at the worst case scenario, but usually elliptic and more simple ones. But if you see in this example I gave, it's not exactly rough, which means that when this parameter epsilon goes to 0, the g function does not change. So what happens if this function g changes as epsilon goes to 0? That's the main point. We are interested in the following class of domains. I will for now get the 2D case because it's a lot more simple to deal in a lot of contexts. But you can think at 3D, 4D, any dimension. So I will point out the differences. So now in this kind of domain, perturbation, notice that when the parameter epsilon goes to 0, the g will change, so we will have a little bit wild behavior, okay? So, and of course, this alpha parameter is positive, and this epsilon is small enough. So, according to the parameter alpha, we have some different behaviors, okay? So first, if we have this alpha small, let's say, we will have something more like this. So alpha will be, and let me call it g epsilon of x. So, and this is of order epsilon. So notice that when alpha is smaller than 1, it oscillates the upper boundary, but it's not wild. It's not a bad kind of perturbation. So it simplifies a lot of things, and it's almost like the standard thin domain case. The most interesting case is this one, when alpha is equal to 1, which means that something like this. So This will have order epsilon multiplied by something I will show you soon. And this also has the order epsilon. For this case, in particular, we need homogenization techniques. Maybe some of you are aware of it. For the case of perforated domains and so on. Here we need to adapt those methods in order to treat this. And of course, due to the generality of the method, we will be able to analyze all the cases of oscillation. So, in this case, what happens now? The order of oscillation is this for alpha. Of course, here also is the same. And this is of order epsilon. In this case, what happens? Here, notice that when epsilon is very small, the distance here is a lot smaller than this one. So basically, if you think of a fluid or anything, what will happen when a particle gets in here? You can see that the particle, if it gets in here, it will fast get out very soon. So it will be bit, and it will leave this rough part. In general, for the heat equation, like Poisson equation, Stokes equation, and so on, usually what happens? Since the particles skip from this region very fast once it gets in, we expect that the flow, the behavior of the temperature, and so on, can be neglected in this region, which means that in the limit, it will disappear, and that's precisely what happens in here. So the limiting behavior will be somehow determined by this region that does not oscillate, let's say like that. So, as I was mentioning, in this kind of domain perturbation, we can study a lot of different problems. Usually, the ones I have work and the ones I am very aware of is this. So this will be in our epsilon. This will be on the boundary. We can also think about this. Or the Navier-Stokes, okay. Here is in our epsilon. And the boundary condition, we can put the standard one. For simplicity, of course, the boundary conditions in both cases we can change. Some recent works we consider the Robin boundary condition here, and it changes the behavior of the limiting problem, but let's not talk about anything like that for now. The methods presented usually during the course, what was? Basically, you guys aimed to construct, like, let me sketch here, asymptotic expansion of the for the solution formally. And usually there would be just one scale, which would be the compression, yeah? Now we don't have it anymore. We have two scales. So it's something like this. Of course, for the heat equation. Poisson, sorry. It will be something like this. For the Stokes, this changes. What changes is the power of epsilon, which you will start usually in 2 for the velocity. The pressure is like this. And so usually you guys do this, find the formal limiting problem, and then try to prove the rigorous result through error estimates, right? In our method, the one which I'm most used to, it's not like this. We usually are, where's the, oh, it's there, okay. Yeah. Usually, the way I am used to study is not like this. So, what we do is basically try to look at the problems. Let's say for now, the Poisson, which I will call a P for simplicity. We usually try to look at the variational formulation. I guess most of you are aware of it. For all phi and the Sobolev space H1. But we have some problems in this formulation. First, you have 2 things varying: the domain and the solution. We can't pass to the limit in this kind of situation. So, what's the solution usually is thought for more than 30, 40 years? We have to find some way to fix the domain to some, let's say for now, a bar R, which will obviously affect somehow the solutions and the test functions of our problem. And then, of course, since the domain of the integral is fixed, we can pass to the limit, but we have some price to pay. What's the main issue for the unfolding method? Once you can fix this domain, it's it's a lot simpler to pass to the limit. But the price is the functional framework that we have to develop. And so that's what I will try to focus for now. So in order to do this way to fix the domain, I will put some notations first that are a little bit heavy, but it's quite good enough. So notations and hypothesis. So notice that I didn't say anything for now about our G. That's what I will try to do. So first, the hypothesis on G will be something like this. So G is a function, a real function. It is L infinity. It is positive. L periodic. One remark here, since we are getting a function on the line, if we got something like this, we would say L periodic in the sense of blocks, okay? Rectangular blocks. So you can extend periodically like this, okay? So it doesn't change a lot. But anyway, and there are constants, G1 and G0 positive, such that where the G0 is the minimum of G. Moreover, G of x0 is less or equal to the lim in as x go to x0. So it's the function G is lower semi-continuous. Notice that since we are supposing this, we are not expecting a lot of regularity of the upper boundary, which is a very powerful thing. We can consider non-smooth boundaries, and this is very general. Of course, maybe there is some price we have to pay here, for example. Usually, if I'm not wrong, the boundary has to be at least Lipschitz for the uniqueness of solution of this, if I'm not wrong. But this is not the case. It just needs to be bounded. So we have a very good tool here. For other methods, maybe you guys are aware, which is the Tarta method, we will use it somehow, and the extension operator and so on. Usually you need that this function is at least C1, which is a lot when you consider the regularity of this function. So, continuing with the notations, and now this is just the first hypothesis. I guess it's the only one with exception to F, but we denote the basic cell. I will explain what is this by y star as usual in the notations. So it will be something like here. So, of course, notice that since the G0, which will be the minimum of G, is strictly positive, the domain can't disconnect, okay? You cannot have something like this, touching the origin. So you have some kind of space that will always exist. Of course, if it disconnects, you will have a lot of problem. Nothing basically works here. And of course, this is an open set, as you all are aware. We also use the following notation for a Sobolev. I will shorten a little bit, okay? I will not get into the details of this kind of space, but its functions in this Sobolev such that phi is L periodic on its first variable, okay? Let's say like this. It's not the best, but it's good enough way to understand. Also, I will denote this as the average, okay, as usual. Some people denote in another way. I don't like to use bar because sometimes it's easier for notation in the text. So, One important remark here regarding the function g, I was always forgetting to mention. So consider first the following kind of function, like, I don't know, a constant b plus 2. So I will call it g1. And the function g2, which will be and b plus 1. So it's a little bit obvious that these two functions are equal almost everywhere. Okay, so almost everywhere in 0L, but they're not exactly equal everywhere. So what happens here? In one case, we will have something like this. Okay, we'll have something, let me put a hole here, and the other, the entire one. Even if they are almost everywhere equal, they do not generate the same basic cell. Okay, and this is an important feature because you can consider, as I was mentioning, very general domain perturbations, and it will make this differ from the rectangular box. Why? As you know, if you have a simple rectangular box, it will be the standard time domain without oscillations, and you can treat in a lot simpler way than presenting all these tools, okay? So, I will not need anything there. So, let me keep going with notations and ideas. Okay. So, as I was saying, if we have these like functions like this, or functions that are periodic and depends on the first variable oscillating, we have some things to present. So, for example, how we can generate our epsilon using the basic cell. How? So, recall that what we have to do. So, if the basic cell is something like this, okay, so it's 0L, it's the G of Y1, I will erase it soon, it's something like that. So, in order for you to have the R epsilon, which is the 0, 1, and something like this, notice that somehow you have to rescale that to make it fit in a lot of ways here. And what happens? So, how to rescale? Because you have this, okay? Note that here, let me put this a little bit below. If you multiply it by epsilon alpha in the horizontal direction, this will change. So you will have something like this. And what more? You will need to multiply by epsilon in the vertical direction. So we will have something like this. So you can make copies in the horizontal direction. So what will happen? you will be able to generate the R epsilon somehow like this. So, and so on, okay. I will stop here. And so on. And then you will have the resulting, let's say it stops here, not exactly. So you will have something like this. This will be an important feature for the method, okay? And how? Let's put some notations here. Notice that if you have a point in the domain, now you can think of it as R epsilon. I guess everyone agrees that there is, let's say, a natural number that will depend on epsilon and the point somehow, such that this point x, let's say it's like here, it will be this natural number multiplied by the epsilon alpha and multiplied by L. So plus something that is between 0 and L somehow, okay? So let's say, I don't know, z of x. So where this zx is between 0 and L. I guess everyone agrees with this, yeah? So this will induce us to consider the notation of biggest integer. I guess you all remember from the undergraduate courses. So for this kind of expression, we will write it like this, okay? So we will have the power of epsilon, the notation of biggest integer, and the period plus okay. So we have the notation of biggest integer. This will play an essential role when we define the unfolding operator. Here, oh, there's no other color, then no problem. So next, basically the last notation is the following. Notice that we will have a quantity that we can enumerate of basic cells rescaled, forming the domain. But there is always, in general, of course, let's say something remaining. Agree? Because you will have an integer number of cells scaled, but not always it will be integer. We will have always a remaining here. This somehow gives us some problem, but it's solvable. But it's important to mention. So let's say this integer part here, so I will put 3, this cells which is integer, we will call R epsilon 0, okay? And this remaining here, which I will put something like this, we will call R epsilon 1, which is the remaining from the R epsilon. Mathematically speaking, we basically have the following. The interval 0, 1 is written as the union. Let the interior of the union from I to 0 to some integer which is basically here, okay? Union now let's put some here, it's better, yeah. Okay, I guess you all agree we can write the horizontal part as this, okay? We will have this and this, each one, and this last one remaining. This part I will call I epsilon, and this big lambda epsilon. So, finishing the notations, to understand deeply the notations, we have that our epsilon 0 will be dxy such that x is in I epsilon and 0 okay, so it will be this left part. No, I mean, that's why I took off one less here. I put one more here and take one last.
The last part is ends with.
I mean, it's as you wish, because you can consider the one more here and take. Okay.
I don't understand, because it has n epsilon plus 2 here at the end.
Yeah.
Oh, okay. You can. You want here, or what do you mean?
Minus 1, I think.
Up here?
Yeah.
Oh, okay. No, I mean, if you consider one, if you consider this one here, you should get one minus here. Anyway, it's a small thing to fix. Because the last one will be, for instance, in this, yeah.
There was an overlap, and then it counted 2 times.
Oh, okay, yeah. Okay, thank you. And there's 0, y. So, you have this remaining, let's say like this. After the notations, finally, we can introduce the unfolding operator. So, finally, the first mathematical definition, I will abbreviate it here. So let phi be a function, a measurable, okay? Measurable. I guess I forgot to put this notation. A measurable function in R epsilon. The unfolding operator d epsilon, which will take measurable functions in R epsilon and we'll have functions also measurable. Here is defined by oops, I forgot, acting on phi is so the variables from the basic cell, I guess if I erase it here, will be exactly like this. So I will put in a little below. I guess no, it will not be enough. A little bit more to the left. It will be the phi of here on that I just presented, and 0 here. This is the definition of the unfolding operator. So, some remarks, I will not write it, but it's important. Suppose that phi has some regularity, okay, you see 1 or anything. Since you get the biggest integer here with respect to x, you can't derivate this part, yeah, as everyone knows. But you will be able to take derivatives in y1 and y2, yeah, with no problems, with no lost. Basically what happens, all the regularity that phi has will be inherited by the t epsilon of phi as a function of y1 and y2. This is something very important, and this is what will give us a lot, actually. And moreover, notice that due to this kind of behavior, if you have an x here and you have another x here, the biggest integer will be the same for both, yeah? For every point in this basic rescaled cell. So, if you, I don't know, I sorry, I won't be able to make a draw of it, but for a class of x's, you will have the same value, the same biggest integer, so you will have something like, let's see if I can draw this, at least this part, because I'm not a very good drawer. Something like this. So you will have for one of these here, and here is y2. You will have this, and of course you will have something like you get overlapping this for some x here. I don't know how to draw it properly, sorry. I guess you can imagine somehow. So, but this does not explain my initial idea. How does this thing will help us to fix the domain? It doesn't look like, yeah? I will state the proposition, try to prove the main, the principal one, and then I guess, yeah, I will talk a little bit more and then stop. Okay. I will let some parts of it for here, especially this draw. I will use it to explain the proposition. So, proposition 2. T epsilon satisfies first. It is linear with respect to the multiplication operation and the addition operation, okay? As is obvious due to this definition. The second, if we get a function defined in R epsilon, so we will have this. Okay. Oops. Oh, here can be infinity. Yes, can be. The part number 3 is very common in homogenization. So if you take a measurable function in the basic cell and you rescale it, extend it periodically like this, not without the powers of epsilon, and then so let this and extend it periodically in the first entry. Define phi epsilon sorry, then is in here. This is all very common. Basically, the justification is here, that this is also measurable. And moreover, if phi is an LP, then obviously, right? So before stating the main property, or before proving the main property. So consider a function here. This is the main property. I will try to give an idea of the proof. So it holds that and of course this last here is also equal to phi dy minus so look here that because this is important. So if you recall the beginning, the variational formulation is basically this integral. This integral is part of it. What this property is saying to us is that we can rewrite that part rescaling with 1 over epsilon, which is expected because the domain shrinks to the segment line. We can decompose it, rewrite it as this integral over here, which is in a fixed domain now. We will be able to pass through the limit somehow. Plus this term here. Usually we can call it integration defect, okay? What we expect from this integration defect? We expect it to converge to 0. And notice that it makes sense because, I mean, suppose that this is the last one. We have something of order epsilon to the power alpha here in the horizontal, and you have something of order epsilon. So this order epsilon in the vertical variable will erase with this one somehow, and the other leading term, which will be the horizontal, will make it goes to 0. Let's say formally. Okay. We have to prove it, but that's basically what happens. This is the most important property of the method, I would say, in my opinion at least. So, if you look at these properties for now, what would be somehow expected to be state, sorry. If we have something like here, we expect that the unfolded function will be somehow in the LP of something. And this is what we will state here. And then we say something about the derivatives, okay? This is therefore. So, if the function is in LP of R epsilon, then the unfolded phi is in an LP times y star, as expected. Here I will not talk about the L infinity, but anyway. So I will exclude the infinity for now because I guess I won't use around here. Moreover, if we take the norm here, we will have something like, okay, yeah. Yep, due to this property. Notice that we use the inequality from here to here. Since this R epsilon 0 is into this of course. This is the r epsilon 0, this part with the 3 here. And it's less or equal to the norm in the whole domain. Okay? This is very easy to see. 6. And the last property, if we have a function, let's say it doesn't need to be in W1P, but it can be W11 to state this proposition, but anyway. So if we take the derivative of the unfolded function, I guess I erased the definition. If you look back in the definition, inside here will be something like, will be this, okay? Will be this. This is basically the unfolding on the remaining of the domain, it's 0. So when you derivate in y1, the epsilon alpha goes out as expected, and we will have the derivative in x of phi, okay? For the second, just the epsilon goes out. And basically this is the main properties of the unfolding. Of course that if you have a Sobolev function, you can put this and this, the last two properties to get the relation between the W1P norm, okay? It will appear an epsilon, a power of epsilon in front of the W1P norm. So, yeah, I will try to make a sketch of this, and then I will stop because it will be tiring. Oh, I shouldn't erase this figure, I draw it again. Okay. So, all the properties are very simple to prove, with the exception of this one, which is the most important. So, I will to make a little bit of the proof, just for the property 4. So, what happens? So let phi in L1. So the starting point will be this. I will drop the differentials here, okay? I will put it again in a few more equalities. So, recall that the unfolding of the function is this, and is in I epsilon times y star, and 0 in that remaining of the draw I just erased. So, this will be the I epsilon of what? Now I will need. So I don't know if it will fit here. So of L, oh it will. Dx, d big Y. Here this, oh I forgot to mention here, this d big Y is like, to reduce a little bit the notation, okay? It's this differential. And now we use the definition of. Okay, sorry? L? Where? Oh, 1 over L, yeah. Oh, here, okay. Thank you. Now we use the definition of I epsilon. So if you recall, it will be so here, for now, I'm just making the copy of the I should do here. So this is now the smart step. How? If you recall that figure, I just erase. What happens? You have this, okay? And so on. And what's the notation of this thing? This is the biggest integer. So for each one, we will have here, okay, for each integer of the summation, we will have here. And moreover, notice that this summation, we are taking index, natural index, natural numbers here, which is of course this natural integer for each one will be this. I guess you all agree with it, yeah? Each of these natural integer here that appears in this summation is exactly equal to this one, yeah, due to this decomposition. So what happens? You will have d1 over epsilon. The summation I will not write. And what we can do then? We are able to write it. Let's copy for now. 0L, 0G of phi of epsilon alpha. We change this by I. Okay. What happened in here? We got rid of the dependence of the x. Okay. Doing this. So what will happen now? Since I got rid of this dependence on x, we can simply put this minus this, which will be, and since here is the summation between 1 and so let me put it epsilon alpha times L, okay, which is the difference, the integral here, just this. And now the last thing to do is considering a change of variables. We will call this x and we will call this y, which are the variables of the original domain R epsilon. So what will happen? I cannot drop the summation. If I call it all of this x, I guess you all agree that what will appear is this integral here, okay? It's between these and these quantities, okay? If you call this x. This is what's going to appear. So, and moreover, notice that if you isolate y1 here, what will happen? You pass the epsilon dividing, so you will have this minus I multiplied by L, okay? This is y1, which we will substitute here in G, but what's the good thing? G is L periodic. So the G of y1 will be the G of this, which is, since this is the period, by I, okay? So basically, and of course this ray scaling will make an epsilon multiplying the G appear here. By the phi. And of course, since we get this change of variables, what will appear? I guess you agree that there will be an epsilon alpha dividing due to this, okay? So derivative, the dy will be the dx over epsilon alpha, and the dy2 will be dy over epsilon. So it will appear this, yeah, outside. Of course, these two things drops, and then we rewrite this summation here as the integral over r epsilon 0 or this. And this is the main property of the unfolding operator.
I have a couple of questions. First of all, why does this epsilon appear in front of G?
Oh, which one?
I mean, the last.
Here?
Yeah.
So, you have that this happens, yeah?
The G is directly replaced by G of epsilon.
Sorry?
This G of y1. You wrote down that it's replaced by this.
Oh, yes. What is inside?
Yeah, okay.
Yeah.
But why does this epsilon appear in front?
In front. Oh, this one here.
Yeah.
So, yeah. So I called the yeah. So the y will be between 0 and the epsilon times the G, because the extremes of y2 are 0 and G. Okay. It's from the change of variables. So if y2 is between 0 and G.
It's not confusing to call this x if you eliminate x in the.
What x?
This new variable.
Oh, this new x?
Yeah.
Oh, I mean, oh, okay. Of course, for a question of notation, probably should be x prime, yeah. Yeah, okay.
It's a bit confusing.
Okay. So it's okay, or anything? So, of course, since r epsilon is the interior of we have that the last so basically that's it. There are some proofs maybe we can do on the next few times. Probably I won't. It's very technical and we would invest too much time. But the heart of the method, in my view, is this property. If you understand this one, the remaining parts, I guess, becomes a lot simpler. And this is the hard part, actually, to understand. This is just a few calculations, in my view. So, one last remark. Oh no, I already did it, so that's no problem. So the next thing of studying, next to two things. We'll be proving that this will converge precisely to 0, and to study the convergence properties of the unfolded sequences of solutions of problems we will consider. I will try to focus on the Poisson problem and the Stokes problem in these lectures. So that's it. I will stop here. If you have any questions, please.
It's slower this time.
Oh, okay.